So let's just see how it works on the same example we traced through earlier. So we start out just by initializing things in the obvious way. So the shortest path distance from S to itself we say is 0, and the shortest path from S to itself is just the empty path. And initially our X is going to be just the source vertex itself. So now we enter the main while loop, and so remember in the while loop we say, well, let's scan all of the edges whose tail is in the vertices we've already looked at, whose tail is in X, and whose head is outside of X. Now in this first iteration, there are two such edges. There's the edge S, V and the edge S, W. So how do we know which of these two to choose? Well, we evaluate Dijkstra's greedy criterion. And so remember what that is. Dijkstra's greedy score for a given edge VW that's crossing the frontier is just the previously computed shortest path distance for the tail of the arc plus the length of the arc itself. So at this point, SV has a greedy score of 0 plus 1, which is 1, and the arc S, W has a greedy score of 0 plus 4, which is 4. So obviously SV is going to be the shorter of those two. So we use the edge SV. This is playing the role of V star W star on the previous slide. And the algorithm then suggests that we should add V to our set X. So we suck in V, and our new X consists of S and V. And it also tells us how to compute the shortest path distance and the shortest path from S to V. Namely, in the A array, we just write down what was the Dijkstra's greedy score for this particular edge, and that was 0 plus 1, or 1. It also tells us how to compute the shortest path for V. Namely, we just inherit the shortest path to the tail of the arc, which in this case is the empty path from S to itself, and then we tack on the end, we append the arc we used to get here, the arc SV. So now we go to the next iteration of the while loop. So with our new set capital X consisting of S and V. And now again we want to look at all edges which are crossing the frontier, edges that have tail in X and head outside X. And now we see there's three such crossing edges. There's S, W, there's V, W, and there's V, T. All of those have the tail in X and the head outside of X. So we need to compute Dijkstra's greedy score for each of those three and then pick the minimum. So let's go from bottom to top. So first of all, we can look at the arc S, W, excuse me. And the greedy score here is the shortest path distance for the tail, so that's 0, plus the length of the arc, which is 4. So here we get a 4 in this iteration. Then if we do this crossbar edge, this VW edge, the Dijkstra greedy score is the A value, or the shortest path distance value of the tail, and we computed that last iteration. The A of V value is 1. We add to that the length of the arc, which in this case is 2. So this edge V, W has a score of 3. Finally, there's the arc V, T, and here we're going to add 1, which is the shortest path distance of the tail of the arc, plus the edge length, which is 6. So that has the worst score. So since the edge V, W has the smallest score, that's the one that guides how we supplement X and how we compute the shortest path distances and the shortest path for the newly acquired vertex W. So the changes are, first of all, we enlarge X. So X is now everything but T. And then how do we compute things for W? Well, the shortest path, so our entry in the A array, is just going to be Dijkstra's greedy score in the previous iteration. So that was 1 plus 2, so that's going to be equal to 3. And then what is the shortest path? How do we fill up the array B? Well, we inherit the shortest path to the tail of the arc, which in this case is the arc S, V, and then we append the arc that we used to choose this new vertex W, so that's the arc VW. So the new path is just the S, V, W path. Okay, so that's what we compute as the shortest path from S to W in this graph. So now we proceed to the final iteration of Dijkstra's algorithm. We know what vertex we're going to bring into X. It's going to be the vertex T. That's the only one left. But we still have to compute by which edge we discover T and bring it into the set X. So we have to compute the greedy score for each of the two crossing arcs, V, T and W, T. And in this final iteration, the score for the arc VT is unchanged. So this is still going to be the A value of its tail 1 plus the length of the arc 6. So the score here is still 7. And now, for the first time, w comma t is a crossing edge of the frontier. And when we compute its score, it's the a value of its tail w, which is 3, plus the length of this arc, which is 3, so we get a greedy score of 6. So by Dijkstra's greedy criterion, we pick the edge wt instead of the edge vt. And of course, that doesn't matter who gets brought into x, but it does matter how we compute the a and b values for t. So in the final iteration, we compute at to be the Dijkstra greedy score of the edge that we picked, which is the edge wt, and the score was 6. So we compute the shortest path distance from s to t to be 6. And then what is the path itself? Well, we inherit the shortest path to the tail of the arc that we used to discover t. So that's the shortest path to w, which we previously computed as being the path through v. And then we append the edge we used to discover t. So we append the edge wt. So the shortest path from s to t we're going to compute as the zigzag path. S goes to v, goes to t, goes to w, goes to t. And then now, indeed, x is all of the vertices. We've computed it for everything. This is our final output. The contents of especially the A array, is the final output. Shortest path distances from S to all of the 4 possible destinations. And if you go back and compare this to the example you went through to the quiz, you will see, at least on this example, indeed, Dijkstra's algorithm corrects the shortest path distances. Now, I've said it before, I'm going to say it again. If someone shows you their algorithm works just on some example, especially a pretty simple 4-node example, you should not jump to the conclusion that this algorithm always works. Sometimes algorithms work fine on small examples, but break down once you go to more interesting, complicated examples. So I definitely owe you a proof that Dijkstra's algorithm works not only in this network, but in any network. And actually, it doesn't work in any network. It's only going to work in any network with non-negative edge lengths. So to help you appreciate that, let's conclude this video with a non-example showing what goes wrong in Dijkstra's algorithm when you have networks with negative edge lengths. So before I actually give you a real non-example, let me just answer a preliminary question, which you might have. And this would be a very good question if it's something that's occurred to you. The question would be, well, why are these negative edge lengths such a big deal? Why can't we just reduce shortest path computation with negative edge lengths to the problem of computing shortest paths with non-negative edge lengths, right? So why don't we just sort of clear things out? We just add a big number to all the edges. That makes them all non-negative, and now we just run Dijkstra's algorithm, and we're good to go. So this is exactly the sort of question you should be looking to ask as a computer scientist, as a serious programmer. When confronted with a problem, you always want to look for ways to reduce it to simpler problems that you already know how to solve. And this is a very natural idea of how to reduce a seemingly harder shortest path problem to one we already know how to solve using Dijkstra's algorithm. The only problem is it doesn't quite work. Why doesn't it work? Well, let's say you have a graph and the most negative edge is -10. So all the edge lengths are -10 and above. So then what you'd want to do is add 10 to every single edge in the network. And that ensures that all of the edge lengths are non-negative. Run Dijkstra's algorithm, get your shortest path. The issue is that different paths between a common origin and destination have differing numbers of edges. So some might have 5 edges, some might have 2 edges. Now, if you add 10 to every single edge in the graph, you're going to change path lengths by different amounts. If a path has 5 edges, it's going to go up by 50 when you add 10 to every edge. If a path has only 2 edges, it's only going to go up by 20 when you add 10 to every edge. So as soon as you start changing the path lengths of different paths by different amounts, you might actually screw up which path is the shortest. The path which is shortest under the new edge lengths need not be the one which is shortest under the old edge lengths. So that's why this reduction doesn't work. To be concrete, let's look at this very simple 3-vertex graph with vertices S, V, and T and edge lengths as shown, 1, -5, and -2. Now, what I hope is clear is that in this graph, the shortest path, the one with the minimum length, is the 2-hop path, SVT. That has length -4. The direct ST arc has length -2, which is bigger than -4. So the upper path is the shortest path. Now suppose we tried to massage this by adding a constant to every edge so that all edge lengths were non-negative. We'd have to add 5 to every edge because that's the biggest negative number, the VT edge. So that would give us new edge lengths of 6 and 0 and 3. And now the problem is we've changed which path is the shortest one. we added 10 to the top path and only 5 to the bottom path, and as a result, they've reversed. So now the bottom path ST is actually the shorter one. So if you run Dijkstra on this graph, it's going to come back with the path ST, even though that's not in fact the shortest path in the original network, the one that we actually care about. Okay, so that's why you can't just naively reduce shortest paths with negative edge lengths to shortest paths with non-negative edge lengths. Moreover, on this very same super simple 3-node graph, we can try running Dijkstra's shortest path algorithm. It's perfectly well defined. It'll produce some output, but it's actually going to be wrong. It is not going to compute shortest path distances correctly in this graph. So let me show you why. Well, so of course the initialization will work as it always does. So it's going to start by saying the shortest path distance from S to itself is 0 via the empty path. And then what's it going to do next? It's going to say, okay, well, we need to enlarge the set capital X by one vertex, and there are two crossing edges. There's the XV edge and the ST edge. And what's it going to do? It's going to use the Dijkstra greedy score. So the score of this upper edge is going to be 1, and the score of this bottom edge is going to be -2. Because remember, you take the previously computed shortest path value of the tail, that's 0 in both cases, and then you add the edge length. So the edge lengths are 1 and -2, so the scores are 1 and -2. Which of these is smaller? Well, evidently, the ST arc has the smaller score, -2. So what is Dijkstra's algorithm going to do? It's going to say, yes, let's go for this edge ST. Let's bring T into the set capital X. T is now part of the conquered territory. And of course, as soon as you bring a node into the set X, into the conquered territory, you have to commit, or Dijkstra's algorithm chooses to commit to its shortest path distance and its shortest path. What is the definition of its shortest path distance as computed by Dijkstra? Well, it's just its greedy score. So it's going to assign the vertex T the shortest path distance of -2, and the path is going to be just the arc ST. But notice that this is in fact wrong. The shortest path distance from S to T is not -2 in this graph. There is another path, namely the one that goes through V, that has length -4, less than -2. So Dijkstra computes incorrect shortest path distances on this trivial 3-node graph. So to summarize the story so far, we've described Dijkstra's algorithm. I've showed you that it works in a very simple example that doesn't have negative edge lengths. And I've showed you that it doesn't work in an even simpler example that does have negative edge lengths. So I've both given you some plausibility that it might work generally, at least for non-negative edge lengths, but I've also tried to sow some seeds of doubt that it's not at all clear at this point if Dijkstra's algorithm is always correct or not, even if you have non-negative edge lengths. And certainly if it is always correct, there better be a foolproof argument for why. You should be demanding an explanation of a claim that Dijkstra's is correct in any kind of generality. That's the subject of the next video.